Welcome to our course on stochastic processes. Today we're going to lay some foundations for later chapters, and we will be dealing with so-called filtrations and stopping times. As you know, our probability space we're always dealing with has a sigma algebra, which we usually call F or so, and a filtration is a family of sub-sigma algebras. That sounds actually more complicated as it should be, because you can basically think of Ft, one of these members of this family, as the information available by time t. I'll explain that using my slides. So let's get started with filtrations and stopping times. Of course, we first have to say what a filtration and a stopping time is. So let's start with the filtration. We have our probability space omega fp, and a filtration is a collection of sub-sigma algebras, which is increasing. So ft is this family, and fs is a subset of ft for s smaller or equal than t, and that is already a filtration. A very generic one is the filtration generated by a stochastic process. So xs are random variables, say they generate sigma algebras. And if you take all xs, s smaller or equal than t, well, that's a sigma algebra, and that is also going to be an increasing in t family of sigma algebras, which is a filtration, and that's the filtration generated by x. On the other hand, we want to say something that a stochastic process is somehow compatible with a filtration, and that's the notion of adapted. So if xt is ft measurable, then x is called adapted. Okay, so in particular, that means that every stochastic process is adapted to the filtration generated by itself. That makes sense, I guess. Okay, then let's come to stopping times. Just a second. So what's a random time? We have stochastic processes like this here, time here, xt here, and xt is that's somewhat ugly. So xt as on the y-axis here, so on this axis here, but we can of course also have random variables on the other axis, on the t-axis, and these are random times. So a bit more exact in the completion of I. So for example, a random time could also take the value infinity or something. So that's a random time, and it's a stopping time with respect to a filtration ft if well, let me say one more thing about filtrations. So ft is somewhat the information which is available by time t. You can see that very well here. So in the filtration generated by x, ft knows everything about x up to time t. So the information up to time t is available. And for the stopping time here, by time t, you have all information up to time t, and you should be able to say if the stopping time is less or equal than t, which in these probabilistic terms is the set t smaller or equal than t is in ft. So that's the stopping time, where you also can have equality here, and it's a so-called optional time if you can only decide if it already occurred before time t. Every stopping time t defines a sigma algebra, which is the following here. That's a set of A with a property that A intersected with stopping time less or equal than t is in ft. So A together with the stopping time has already occurred by time t can be decided with information up to time t. And here's something which will keep us busy also for today and the next time. The stopped process. So I evaluate x at time t, so at the stopping time. So one simple example. I have a brownie in motion. Let's start that in 1. And eventually it will hit 0. And I call the random time t, where it's hitting 0. So t is here the infimum over all t, xt equals 0. And of course, I then have x evaluated at the stopping time is 0, because that's exactly how I did that. So that's the random variable evaluated at the random time. And the process stopped by time t. This is the process which goes as usual before time t, and then it stops, which means it's a flat line after that. That's the stopped process. So that was an example about brownie in motion, but let's first look at the Poisson point process. First properties of stopping times. No, I was too fast. Here, hitting times in the Poisson point process. Here we are. So recall that we had in the last video, or the second one? Yeah, here. The left and the right continuous Poisson point process. So that was left continuous, and that here was right continuous, which were called x and y. And for example, we have the stopping time, the first time where xt equals 1. And it doesn't matter if it's xt here or yt, because as you see here, well, the times are just the same. It's just the value at that time is either 1 or 0. But I claim t1 is an ftx stopping time for the right continuous version, and also an option time, but it's a bit different for the left continuous Poisson point process. So we have here x at time t1 equals 1, but y at time t1 equals 0, because the y process at the first jump time is 0. And t1 less or equal than t, well, it's important to see that that's the same as xt bigger or equal than 1. And xt bigger or equal than 1, that's in the sigma algebra generated by xs, s less or equal than t, which is ftx. And t1 smaller than t, well, what is t1 smaller than t? So t1 smaller than this t here, for example, that's not true. So I have to write it differently. I'm writing it like this. The left limit here, xt minus, is bigger or equal than 1. So at the jump time itself, this one here does not hold, but this here also does not hold, because the left limit is not bigger or equal than 1. This here is in the sigma algebra xs, s smaller than t, which is a subset of ftx, and which is the reason why t1 is also an ftx optional time. For y, it's almost the same. The second line is just the same, except for you have to exchange x by y. But the first line is not the same because this equality here doesn't hold. So at the jump time, yt is still 0. So that's simply not true. So here I would have to say, well, I have to make, it's a y, yt plus bigger or equal than 1. So the right limit. But the right limit, well, the right limit here, that's not measurable with respect to the sigma algebra, because I have to look a little bit ahead of t. And that's the reason why t1 is not an fty stopping time. Okay, so far so good, and so far with some examples. Let's do some theory about stopping times. Some very basic things. Fixed times are stopping times. Well, and that's really easy also to show. Why is that a stopping time? I take some t, and I say the stopping time, which is s, smaller or equal than t. Well, that's either the empty set or omega. Well, and this is of course subset of ft, which means that's a stopping time. So that's easy. The second one is a bit more interesting. The minimum of 2 stopping times is a stopping time. The maximum of 2 stopping times is a stopping time. The sum of 2 stopping times is a stopping time. So that's a bit more interesting. So let's look at this here. So some are really easy also. So the minimum smaller or equal than t, what's that? When is a minimum smaller or equal than t? That's the case if either s is smaller or equal than t or t is smaller or equal than t. And both of these events here are in ft, so their union is also in ft. So that's in ft. Similarly, for the maximum, maybe we can just write it also here. So if I have a maximum here, if the maximum is bigger or equal than t, then both have to be smaller or equal than t, like this. So that's also in ft. So I don't have to write anything really. But s plus t, that's a bit more tricky. I write s prime equals s minimum t plus the indicator that s is bigger than t. And the same for t. So t prime is t, t minimum small t plus indicator t bigger than t. And why is that? So first of all, this thing here, so these two things, they are ft measurable because s and t are stopping times, so s smaller or equal than t is in ft, and that's just the complement. So this here is in ft, that's also in ft. And s minimum t, well, s minimum t is also ft measurable because it's Because, well, let's write it here. So now S smaller or equal than T is in Ft. And this random, this random variable I can also write, so S minimum T equals S on the set S smaller or equal than T plus T on the set S bigger than T. Again, this here is Ft measurable, and this one here is also Ft measurable because, well, this is measurable, St measurable, and this is St measurable. Yeah. So all these are now Ft measurable. And the point is that I can write when is S plus T smaller or equal than T, that's the same as saying S prime plus T prime smaller or equal than T. Why is that? So both of these, so the sum of these are smaller or equal than T, then both of them have to be smaller or equal than T. Which means, well, I only have to focus on this here. So the other case, when S is bigger than T, then, well, it doesn't really play a role here for the event S plus T is smaller or equal than T. So that doesn't have an effect at all. And then it doesn't matter if you take S minimum T or S for the sum here. Yeah. So that's the reason for this here. And for these here, we had that S prime and T prime were Ft measurable. And that means that's here in Ft. Okay. Then let's come to the fourth property. New page. T is Ft measurable. And let me just briefly recall what Ft is. That was in the sigma algebra of all A, the property that A intersected with capital T smaller or equal than small t is in Ft. And now I claim that T is Ft measurable. So what does that mean? I have to prove that a generator of the sigma algebra generated by T is subset of Ft. And a generator, these are the sets T smaller or equal than small t. Yeah. That's of course in Ft. And well, since this here is an Ft and T is a stopping time, well, the A here, which is of this form here, has a property that intersected with this in NFT, and that means that T lesser or equal than T is in F capital T. And that means, so these events here generated sigma algebra generated by T, all are in Ft, and that means big T is F big T measurable. Okay. Then the last property, if I have two stopping times, big S and big T, then if S is smaller or equal than T, then Fs is a subset or equal to Ft. Let's see. So I take some set A in Fs and some T. So this here and T in I. I know that the set B, which is defined by A intersected with big S smaller or equal than T, is in FT. Why is that? So that's the defining property of the FT here, so of the FS to be exact. So A is in FS exactly if this here holds. That means this set here is in FT, and that's exactly what I write down here. I have to show that A is also in FT, which means I have to check the defining property here. So A intersected with big T smaller or equal than small t. Well, if big T is smaller or equal than small t, then S is also bigger or equal than small t. So that's the same as A intersected with S smaller or equal than small t intersect with t equal to small t, like this here. This here is in FT. This here is in FT. This here is also in FT because it's in big T is a stopping time. The intersection of two events is then, of course, also in FT, and then we are done because that's the defining property of A being in F big T. So from this, we A in F capital T, like this. Then here's one definition and one result, which I'm not going to prove here, but which are good to know, and you can check the result in the manuscript. We want to have nice filtrations, and the question is, what is a nice filtration? And the answer is, a nice filtration is one which is continuous and complete. What does continuous mean? That means that Ft plus equals Ft, like this here. Ft plus equals Ft, and Ft plus at time t is the sigma algebra generated by all Fs, S bigger than T, and the intersection over all such S. And complete means if it contains all null sets and also subsets of null sets. So which measure do you want to have for a set which is a subset of a null set? You don't really want to say, well, it's not measurable. You want to say that also has measure 0. So that's the set of null sets, all A, which have an n, which is potentially bigger, which has measure 0. And if this n here is a subset of Ft for all t, then you call the filtration complete. And the lemma here shows that if you start with some filtration Ft, you can make it continuous and complete by saying, well, okay, take Ft plus, okay. You also take n and you generate a new sigma algebra out of this. You make that for all t, and that's the smallest continuous and complete filtration. And here it says it doesn't matter where this plus here goes. If it goes here or here, that doesn't matter. So keep in mind, we want to have continuous and complete filtrations, and sometimes that's important. And why are these nice properties? For example, because of this property here. A random time is an option time for Ft if it's a stopping time for Ft plus. Yeah. Well, and in this case, F big T plus, so that's the sigma algebra generated by all times which are bigger than big T. has this property here. So an ft optional time is an ft plus stopping time, which means if you have a complete filtration or continuous filtration, ft equals ft plus, and that means that every stopping time is an optional time, and so on. Okay. First, yeah, let t be an ft plus stopping time. So I'm only going to prove that one direction. So if an ft plus stopping time is an ft optional time. And A intersected with big T small or equal than small t is in ft plus. Then let's look at the intersection of A with t smaller than t, which is, well, there, if big T is smaller than small t, there must be some s smaller than t such that A intersected with t smaller or equal to s holds. And that s here can also be in Q, which makes this here a countable union. So that's a countable union. And all these things here are in ft if x is adapted. No, there's no x. If f is a filtration, because so this event here is in fs, but s is less than t, and fs is less or equal than ft, so we have this thing here. And now, for example, if we take A to be the whole set, we have shown that t less than small t is in ft, which means the ft plus stopping time is also an ft optional time. And the other claim is yeah, well, that's this thing here. So we've just shown this. So ft plus equals this. That's what we want to show. Yeah. ft plus consists of the sets which look a bit ahead of big T. So ft was defined here. And if we take ft plus here, that I'm at f big T plus, yeah, and that's exactly what I start here. When I have ft plus here, and these are, so if I have an A which satisfies this here, I'm in f big T plus, and I've shown here that I'm exactly, yeah, have this property here, and it also goes the other way around. And the other thing which I'm not showing here is that every ft option time is an ft plus stopping time. So that's also just follows the other direction here. But you can read it in the manuscript. So let's come to some more properties of stopping times. So suprema and infima of stopping times. We already had that the maximum and minimum of 2 stopping times is the stopping time, and now we have infinitely many of these. First, we have that if you have a sequence of stopping times, their supremum is also stopping time. And how can we show this? This here is too much. I'm saying that if small t is some arbitrary time, the supremum of Tn less or equal than t is the same as all of the Tn's are less or equal than t. That works, but it does not work if we have an equal less than here, and the reason is so that's wrong because the supremum can equal t, although all Tn's are less than t. But it works when we have this here. And for the third property, it also works if you have inf Tn less than t. That's the same as all of the Tn's are less than t. So that also works for the third property. Because, well, if the infimum is less than t, that means at least one of them is less than t. The only way out to be a bit more general for the second property is if they are stopping times, but which they only take values 0, 1, 2, and so on, so they take values in a discrete set, then I can say the infimum over all Tn is less than t. That's the same as the infimum over all Tn is less or equal than t minus 1. That's in ft minus 1 because, as we just said, an ft minus 1 is a subset of ft. So that's okay. And the last property, when I have these option times and their infimum, then ft plus equals the intersection of all ftn pluses. Of course, the t here is less or equal than Tn for all n. That's clear. That means Ft plus is a subset of the intersection of all Ftn plus. So that direction is okay. The other direction would be A is in the intersection over all n Ftn plus. And I want to show that A is also in Ft plus and Ft plus, so that was as shown in this set here. So we have to show this property. So A intersection T less than T, that's A, and the infimum of all the Tn's is less than T. That means all Tn's are less than T. Well, and now it's easy because we can rewrite it as the union over A intersected with Tn less than T. That's in Ft here by definition, like this here. That's in Ft, and I make a union of this, and that means the whole thing is in Ft. So that means A intersected with big T less than T satisfies this property here, that means A is in F capital T plus. So I've shown both directions. If Ft plus is a subset of the right-hand side, and if I start with a set in the right-hand side, I end up with A is in Ft plus, which means I have shown this equality here. So let's come to some more examples. Hitting times are very often used for option and stopping times. The hitting time of some measurable set is given by Tb as an infimum over all T, xt is in B. And assume x is adapted. Tb is a stopping time if I equals a discrete set. If it's a continuous set and B is open, x has continuous paths, it's also an option, it's an option time. And if B is closed and x has continuous paths, Tb is also stopping time. Okay, so let's try to prove this. Let's do it on this slide here. First property, Tb less or equal than T. Well, there must be some s less or equal than T with the property that xs was in B and this here is in Ft, because all of these here are in Fs, which is a subset of Ft. So that was easy. For the second, we have Tb is an open set, B is an open set, and I want to have the Tb is an option time, so I have to check Tb less than T. So when am I in an open set and I have right continuous paths, I claim I must be in B for some time s less than T. Yeah, so if Tb is less than T, I find some time before T, such that I'm in the set. And I'm right continuous, which means I can choose these s here in Q, which makes this here a countable union of sets which are in Ft, so that's in Ft then. So that's okay, and for closed B and continuous paths, I want to have the Tb as a stopping time. I'm doing the following. First, I have to set a small ball around B. That's the set of x. The distance of x and B is less than 1 over n. So I'm making a very small epsilon ball with radius 1 over n around B. And then I can say Tb less or equal than T means I have to have hit Bn before that sum for all n. And here I need the continuous paths as well as the closedness of B. So assume I hit my set B exactly by time t. Then this here of course also holds because I hit Tbn sometime before time t. Like this here. And this here, so what does this here mean? So Tb
n less or equal than t, and the bn's are open now. So either tbn is less than t, or xtn is in the closed hull of Bn, like this here. And the first thing here, so that's in ft, because tbn is an optional time. So that's an ft. Sorry, not xtn here, I need xt. So y time t in here. Well, and that's also in ft. So the whole thing here is in ft, and I'm done. Okay, that was it for today with stopping times and filtrations. And next time we come to a small chapter about progressive measurability. See you then.